Okay, apparently I went live before I was ready to go live. At some point, I will get a little better at this whole YouTube thing. Anyway, welcome to Old School Coding, where I am using tools from the 1990s to construct a simulation of a computer from the 1990s. So, C99 and Emacs and GCC and none of this modern crapola, right? Okay. Anyway, a lot of the more modern techniques turn out to have been reinventions of older techniques. So I'm going to go back and basically do old school stuff here, and you will see little bits of the beginnings of new techniques that will, from time to time, pop up their heads. You will also see old ways of doing things, and you'll see why they motivated the new ways of doing things. And maybe we'll just have fun exploring the mad lads at Intel and how they designed the 8080. And oh my God. So yeah, not billions of transistors. So there we go. So our first order of business for the day, just to remind, the previous episode we went in and did a whole bunch of support for instructions that used the M register, mostly the move and move immediate stuff, and it involved basically taking existing instructions, then jamming in a M2 cycle, which would M2 and M3 as necessary, which would arrange to move data to and or from for HL points. And at the end of that, the next step was implementing ALU operations, which are not going to be too hard to implement, but might be time consuming to test. I figured I would put that in a separate stream because it's going to take a while. Now, once we get into just the dog work of writing test cases, if I continue to stream that, I may cut the stream at that point. If I continue to stream that, we may, it's going to be a good point for people to just hit the fast forward button if they aren't interested in watching just iterative working at the salt mines, what we used to call it. Let's get rid of the PDF for a moment. Move that out of the way. So in our document where I'm tracking what I have and haven't done, next up are these 8 ALU operations. So we already have those operations for the 8-bit registers. So B, C, D, E, H, L, and accumulator. And now we need to do it for M. And the difference between doing it with an internal register and M is the internal register, you've got all the data on hand. You can actually do the whole thing in a single machine cycle, because during T4, you can go ahead and latch up all the operands, and then you can defer the write back to the accumulator until the T2 state of the next instructions machine code 1 state, M1 cycle. So yeah, those are all single cycle instructions, but now we have to access memory. And that means that we need a second machine cycle, which does the memory access. All of these are going to be very similar. We're going to continue to use the same T2. Let's jump down to where we define those. So these ALU operations that go in the T2 cycle of the first machine, or the T2 state, so T state number 2 of machine cycle 1 of the next instruction, is going to be performing these 8 operations. And we can look down at that to confirm that what these are doing is they are finishing up the operation based on the contents of the ALU, which is actually what? Oh, right. Let's not look at RLC because we don't RLC the M register. Let's look at something we actually do. So add T2. So here, this is ALU T2 add. So add ADC, these 8 T-state functions are going to be used. So they're basically grabbing their operands from the ACT, which is the accumulator side of the operation, and TMP. And what we need to do is, instead of hooking this up after a M1T4 that moves a register into temp, we need to insert in a machine cycle that grabs from memory and puts that in temp. So I am going to just tuck that in here. This is going to be a machine cycle that reads from memory. Well, that sounds something like a 2-pops, except it's not. Let's go into MOV. And this is really the same thing as a MOV read, except it's not. But we're going to have the same kind of pattern. And we have all these macros, so T4. So before we do the T2, just to remind myself really quick, to do write better comments here. ALU Operations, taking M as an operand, need to do a machine cycle that reads from HL into TMP. So instead of state MOV, this is state, becomes state ALU. And we're going to do a T4, which is going to be the ALU give that a name that I'm sure won't conflict with anybody else. It is static. It's only visible in this file, but it's visible in the debugger. So I try to keep my names at least, they're going to look awkward, but at least I won't have the same name in 2 different files. So ALU T4 read M is actually going to be right here. So we don't need to do anything special there. And we will stick all of the ALU, all of this stuff will just go right in here. Now, these may merge with other things. I will have to consider that carefully as we construct this whole mess. So, the first thing is that this table no longer contains any nulls, so I can get rid of the null check. Now, M1T2, that still holds, because just because we're reading from M into temp doesn't change what operation we're going to do in the T-state 2 of the next machine cycle. So this is still all correct. And now we're hooked up. Now we just need to implement. So we want to step down to this function. And we're going to be surprisingly similar. In fact, we're going to be so surprisingly similar that I think I can simply copy these and then edit them into shape. So we need to change state mauve to state ALU. Let's do that from the top here. And state ALU M2 T2 RD, these become RDM. T1 RD becomes RDM. I could probably edit them in faster by hand. M. Now, in this case, we are not using a dispatch table to get to this guy. We are going to, in fact, have our T3 RDM that. And there's our declaration. Okay, and we have these declarations up at top where they belong. So, comparing with the PDF, which I have over on the other screen, which I'm not going to drop up on this screen because I want to focus on the code here. Well, I suppose I could bring this up and move it kind of off to the side. Yeah, that will work. There. So, ALU operation, we have add R and add M are right next to each other, so we can kind of compare them. During M1T4, add is going to move something into the accumulator temp from the accumulator, and it's going to get our operand. In the case of add from M, we don't put anything into TMP, we just redirect to the proper M2. So there's our redirection to the M2. And we still want to, let's keep this going here, M1T4. We still want to bring the A register into the ACT. Comparing it with the here, A and ACT, and setting our next state. Okay. M2, T1. We put HL and a status word out. And that is correct. HL is being put together in the IDAL and sent off to address. Status M read, and we start the sync, and we head on to the next one. The next one, we release our status word from data, end sync, and raise data bus in, so we want to get data coming in. And this guy needs to be changed to here. Okay, and the wait state is exactly the same. We are asserting wait, and then triggering a rising edge on DBN without triggering a falling edge, and checking ready. Then we get down into the T3 state, and we go down here and we say add M in T3, the data from the data bus coming in T2, T3. I don't know why they drew it all like that, but there we are, is landing in the TMP register. And I haven't yet written this. So this guy needs to do edge low. Remember, this is a copy of the M2 T2. So we'll get the PDF out of the way. So during I8080 mov.c, let's look back here, T3. So here's our typical T3, where we are dropping the weight. We're going to set red M1 int because this is the last T state of the machine cycle that is the last machine cycle of the instruction. That means that we do not do this. So we're releasing weight. We're setting red M1 int. This goes away because that's from the wrong cycle. We are writing to the TMP register, which is going to be picked up during M1 T2. And it uses exactly the same M1 T2 table as the other instructions that do the same operation. So all of the adds are going to use the same function, whether it's add from a register or add from M. So in theory, this should now be working. And I see that it's not actually compiling. Where are we here? So state ALU M2 T3 RDM is here, but for some reason is not being declared. I forgot to put it up here. Okay, ALU T4 RDM. We don't have an ALU T4 RDM. And we should. There we go. This guy needed to be renamed. So that compiles. It runs. We're not going to be working with it. So now the problem is that these instructions will be reading from ROM and writing to RAM. Oh, no, they won't. They will be reading from ROM. We're not writing these back. These are ALU operations that take the accumulator and the memory and put it back in the accumulator. And I think what I'm going to do is I am going to follow these with a write of the result from A back into memory. So we will get that tossed into RAM so that we can do a compare as part of the testing. So now we need to actually start writing test code. And we have our MOVM test. I am going to do this as part of the MOVM test. Come at me, bro. Okay, so this is going to be weird in how it's placed, but it will still do the tests, and it will perform those tests, perform the ALU tests after we've got the MOVM stuff coming. So I think this happens at the right place. Long as we have tested the ALU ops and the move stuff, we can then test the move from M and the ALU ops from M. So our dependency chain is correct still. So what this is doing is it is doing operations on memory. Let's write one by hand. This is going to be add m mov m comma a. And I'm going to just do, because we're using the same bits of code to do the condition flags, this test program is not going to test that the condition flags are set when the operand is m any more than we did a separate test for every other operand. So what I will do is I will do this for each of the 8 operations. Add ADC make sure I have our opcodes up in the other window. Add ADC sub SBB INR DCR INX DCX DAA ANA, and flip to the next sheet on the PDF while I am typing this. Yay, large multiple screens. Did I have multiple screens back then? Yes, I did. When I worked at Sun Microsystems, I managed to finagle 2 screens. Now, they weren't large, but they were 2 screens. And that's where I got in the habit of splitting my working set. So I tended to have my main screen is where I did my editing, and then off to the side, usually on the right, where I kept a screen that had documentation on it. So ANA, XRA, or a CMP. So let's check with the doc i8080.org. So we have add ADC, sub with borrow, ANA, XRA, ORA, and CMP. Bada bink. So now it's a matter of going to the MOVM test program. Oh, this should now be failing that test case. And there we have it. So there's the test case. And RAM test area size has to now get bigger. No, it doesn't. 256 is still way more than enough. I am going to set up a stock thing here. This is going to be OX55 op whatever. So add, this is going to be subtract 11, 12, 13, 14, 15, 16, 17, 18. Three, 4, 5, 6, 7, 8. Oops. So add is going to be 5 plus. Add with carry is going to be there. I think for the add with carry, I'm going to say set carry first. Gee, I hope I've done the set carry instruction. Ha 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 ha. I believe I have. Okay, sub with borrow, which I set SBB up here, STC. Then we have ANA and XRA and ORA, and compare doesn't change the value. So test condition failed here. INRM, DCRM, RST2. Oh, how did that get changed? There we go. And now this condition is failing. And now we're into the debugging part of this work. Well, first of all, let me see if we're actually getting into the code that we should be getting into. I8080 underscore ALU test.c. Oops. O4XHPC. So we're going to do PC and IR and data. We're just going to print them like that. So at 2F. Oh, well, goodness. That's because my assembly code didn't assemble. I never did check that, did I? 0x doesn't exist yet. 0x, we're going to go back, forward by 1, and add a h at the end. So now we see that we're getting through these instructions. Oh, of course, we're not failing until we get to the end of the program and we do the compare. So we are seeing all of these guys are doing a ALU op with accumulator equal to that. Let's actually write this. Okay. Now, in this guy, we're going to say there. So we're PC value -1 op and that, and we're going to do IDAL value here. Actually, no, just do adder. So 9A, B, C, D, E, F, and so on. I'm going to use IDAL in the print so we can print down here as well. going to repeat it here in the T wait and read M. I am going to, after we latch from data into temp, I'm going to do it again. I'm using IDAL here because adder has already been released. So this shows that I am reading from the ROM correctly. We've got a 5.5 from the accumulator, and we've got a temp value of 06 hex. And now I'm going to go down here, and I'm going to specifically say if CPU arrow IR arrow value amper source register, which is in the low 3 bits, 7 is equal to 6. So I'm only going to do this stub when I've got a operand register of 6. And this is going to print out the ACT is O2XH. And TMP and ALU and flags. So PC -1, the IR value, IDAL value, and the registers I am printing here are ACT, TMP, ALU, and flags. Now that's interesting, the order that we're getting these things in, because IR should not already be set up. 17 hex. We are nowhere near that operand. What is going on here? How are we getting to that? How are we getting into T2 add here? That's definitely seeing an opcode C6, which does not appear in the LST file. Oh, wait a minute. Her to her, ALU test. It's not that program. It's this program. So let's go into test i8080 underscore ALU test.c. I'm going to put in, this is ALU BIST add, but it's not BIST that's doing this, it's MOVM that I want to look at. So let's put our prints in so we know that we're in the MOVM test. So these guys, these top two, where we're getting into T2 add, this is not happening inside the MOVM test. So that's that's somewhere else. So let's start from here. Scroll this guy so that we are not looking at things we don't need to be looking at. And we're seeing that we are, in fact, getting into our T2 add at 30 hex here. We've done the add. We're doing the MOVMA. And at this M1T2 of this instruction, we have already incremented PC again. So if I want to do this right, I need to print that to say this is the M2T1, which is sweeping up the results for, oops, no, wrong one. Down here, this guy needs to be -2 because it's been incremented. The value we want +1 again because we're in T2 of the following instruction cycle. There we go. And now we look at this, and there it is. So we're saying that for 30 hex, this MOVMA, oops, that's not right. Hold on. Make sure that built. Yes, it did. One step at a time. 2F here. The opcode is 86, check. The value in the accumulator is 55, check. We're reading from 9, check. We eventually get a 6, that's correct. We can look up here at 9, we can see the 6 is in ROM. And we get down into here. And, oh, right, because the IDAL has already been punched forward. So -1, 2F, this is 2F. We don't need to print IDAL again because IDAL no longer has anything relative to what we're retiring. In fact, none of these guys need to be printed. I can just print the values that are interesting to me, which are accumulator temp is 55, temp value coming in is 6 hex, ALU is 5B, and the flags are 2. And we're going to get down here, and this is claiming test condition failed. Expected value is E4, observed value is E4, and look at this. That's because my test code is wrong. So all of these expected values need to be masked to be within range. There. So that worked. Now we can turn off all the printfs now that we found out that the problem was in the test. And there we have it. So that was a lot less painful than I thought it would be. I figured we'd be spending another hour walking through all of these opcodes, finding various problems. I think I was also thinking in terms of doing some additional testing in here to set flags. I think my initial decision to not try to test all the flag bits for all of these instructions. I basically would have to have out of this add, there's 5 flag bits that need to be compared. Currently, I don't have any way of sending my flag word to memory. Okay. There are ways of doing this, but I have not yet implemented them. You can send the flag word to memory using a push instruction, and we have not done push. So it sounds to me like our next set of instructions are going to be the stack operations. So I'm going to do push and pop next. But let's seal this up and send it to the repository because this is now working. Let me bring up Git Kraken. And I do not know why. There. Sometimes Windows gets a little confused about which window has keyboard input. So this is add ALU operations with M as operand. Test these operations in the movm test.asm file, checking results in the ALU movm test file, test program code. So save all changes. There's movm test. i8080.org, I can now move these items up to completed. This is happening behind the screen. Let me show you that real quick. We're just moving this whole block up above the not yet implemented marker. Get Windows to do the right thing for me. Did I save it? I forgot to save it. There it is. Stage that file. movmtest.hex includes all of the new stuff. There's our LST file. Here is the ALU implementation. Scan this real quick to see if there's anything egregious. All the green stuff looks good. We added our test cases here. Boom, commit. And I'm going to hit the push button. So that's now on GitHub, just in case we have a power failure or something. Well, it's taking a while to push. Okay, what's the dealio? That took a while to talk to GitHub. I have a separate tool I can use to check with this stuff, and it looks like that did indeed get to GitHub. Good. So Kraken now goes back into the background where it belongs. And now we can work on push and pop. So doc i8080.org. So I wasn't going to do push and pop immediately, but let's promote that. Hold on. I have somebody who wants to talk. Be right back. I think maybe she just wanted to say hello. She's not settling down. Did you just want some ribbons? Yeah, she just wanted a little bit of attention. So I will guarantee you that far in the future, when I am on my deathbed and I am regretting my life choices, I will never say, gosh, I spent too much time holding the cat. I will never, nobody could ever say that. So, XTHL is actually a combination of things. What it does is it exchanges the contents of HL with the 2 bytes on top of the stack. So it's kind of like popping and then pushing, and you're somehow holding things in abeyance while you're doing it. And good God, it's going to be ugly. So I'm going to make that a separate instruction, XTHL. I am not committing to doing XTHL. Okay, the other thing I need to do before I get started here is I need to go pour myself some more coffee. I'll be right back. Okay. Coffee is absolutely required because a software engineer is a machine for turning coffee into code and snark. And we prefer to turn coffee into code, but if you force us to go to meetings, we can't code during meetings, so we're going to be snarky. Nice thing about being retired, no meetings. So push, pop. Let's bring up the PDF. Let's look at the actual cycles that go into those. So push is down here. Okay, so M1. During M1T4, we're doing decode, and it's going to decrement the stack pointer, which means copy the stack pointer into IDAL, and then copy IDAL -1, so we decrement IDAL, and we push that back into the stack pointer. During the M2, we put SP out as the address, and it's still actually sitting in IDAL, although the model of the IDAL that I have in my head is that we have data coming into IDAL, and there's an incrementer, which you can either increment or decrement. So there's some code, there's some logic to increment or decrement the 16-bit value. The output of that goes to a latch, which drives the address bus. So you can bring data into IDAL, latch it in, and then increment it and send the incremented data back up to the register pair, which means that we need to hit the address latch again with the incremented data here. Okay? So, whoops, I was on the wrong line. This is push. Okay, we've got a lot of stack pointer related things here. Call and return and RST. All these guys are going to be operating on the stack, which is, it's good that I'm doing the stack now. I know I have to do the stack before I do call and return and so on. There's not a whole lot left to go. We're getting close. So decrement stack pointer, and then we do a memory cycle at SP where we push the high byte of the register pair onto the data bus. And as part of that, we have the SP out during T1. During T2, we decrement the IDAL and latch the result back into stack pointer. Then we have a third machine cycle where, again, we send the SP out and we hit the low byte. This time we don't decrement. It's a pre-decrement stack. So the stack pointer points at the current head of stack. So it's decrement and write. And pop is the other way. So pop is we send the SP out, we send the data out, and we increment stack pointer. So it's write and increment, write and increment. So there we have it. Now I could make these two cycles of SP, I could make these very similar if I decremented SP before sending SP out, but I'm not going to do that. I'm going to keep with the modeling here. So let's do push first. I am moving the PDF off to the side. I will still need to refer to this as we are going forward, but it doesn't need to be on the screen. If I wanted to keep all this on the screen, I would have to basically be streaming the entire 4K monitor at resolution, and then we could go with a smaller font, and we could go with more things on screen, and people wouldn't be able to see it unless they were streaming it at ultra high resolution, which isn't all that good. So, source. We are going to be doing a new test program for source. We're not going to drop this. We've just been appending things into the MOVM test program. This is going to be a new test program that's going to manipulate the stack. Remember, when we do our pops, it's going to be reading what was in ROM at that address, not what we write to memory, because we still haven't hooked up anything to manipulate shadow. Okay? That's going to be a little more in depth, and we could test this stuff without hooking up shadow, so it's not really a requirement. See, I8080 underscore, let's call this stack dot C. Here we go. I'll just say stack operations. Okay, so we have to have an init function. And I need to set up some test stuff. So we go into I8080 stack test.c. And we're going to write something like this. Fetch doesn't have any tests, so it makes a great little thing. I8080 stack test the stack operations. So I-8080 stack, this is actually going to be called with an instance of a test system. So this actually ends up looking more like one of these guys. Let's grab dad test. So the parameters for these guys are this. There we go. And we do a void ts to do implement. Okay. Inc. I-8080 impl. I'm going to find Mavum. I'm going to find dad, and I'm going to put stack after dad. DAD. Okay, there's that. So we've now declared this stuff. We have stack in it. Okay, now we go back to source, and the 8080 will need to, again, wherever we have dad, we're going to put stack after it, and that's just the one. Test I-8080 test. I think I can put my stack tests after Mavum tests. And we are not going to have a stack bench. Okay, so we recompiled the world and re-indented the world, and we have implicit declaration of stack bist. Stack post, I removed that. Literally, I was looking at it and I read the word bench instead of bist. Interesting. Okay, unused parameter CPU. So we put in a void CPU to do implement. So now we know that we are getting into this function, and we're getting into this function, and we're getting here. Okay, so all of our widgets that we need to call up are being called up, and now we have to start implementing, and we will do testing and so on. And the testing, again, is going to be loading up a test program and firing it up. And I am still using the RST instructions for my magic, aren't I? That's not good. I'm still not doing a central thing. So before I implement the RST instructions, I need to do I need to combine all of the things that are using test programs and unify that, and then move over from the RST instructions to some illegal operations. So, stack instructions. Back to the PDF here. Push, 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 push. I'm going to need to have M1 T4s for these guys. F88, is that right? Is that right? Is that right? Source, good bink. Yep, F8080 state. I8080 underscore stack. Should I just call this push M1T4? let's just do push for now. I will do pop shortly. So the push instruction here, we haven't yet diverted out to 1 per register pair. It's kind of like LXI in a way. Byte op is equal to, and push is a 0xC, RP left shifted by 4 and 5. Then we say CPU arrow M1 T4 of op is equal to this guy. M2 T1, M2 T through, T3. This is pushing, so we don't have a T wait. M3. But we have variants of these for each register pair. And push, our writes to memory occur during T3. So we're going to need a macro for that. Fortunately, we have tables for M2 T3 and M3 T3. So now I need to actually set up those functions to be the right kind of thing. Who tells me? Well, we can go back into MOVMs for all of this. MOVM moves stuff to and from memory at HL. We're moving stuff to and from memory at SP, so we're very similar. So let's just grab one of these at random, and I will make a template out of it. Okay, so there we go. Windows demapped my window for a moment there. You damned it. There we go. So we want to grab from here down. Okay. so this can continue to compile, I will line comment out these guys. So M1T4, CPU arrow state next is equal to M2T1. So M2T1s look something like this. There's the phi2 rising part. The IDAL in this case is going to get SP arrow value. Now M1T4, I almost forgot. Let's map that PDF back onto the screen so we can verify this. Push RP, we're decrementing stack pointer during T4 and T5. So we do have a T5 during push. And what I think this is doing is that during the T4 cycle, we get SP into IDAL, and during T5, we have to latch it back. And in fact, we're going to do plus one, minus one here. And then here we're going to go SP is IDAL. That does leave the current stack pointer value in the address latch. How have we done this before? So typically what we've done before is we've placed our value into IDAL and then we've incremented it on the way out. So let's do that the same way we did it here. Try to keep this compiling. Okay, M2T1. We decremented SP up here. So again, SP goes into IDAL here, M2T1. Let's move this off this direction so we can see what we're doing. So here's M1T4, where we get stack pointer into the IDAL. And here we take the decremented IDAL back into stack pointer. And I'm going to leave IDAL alone. I could Z it out, but I'm not going to. Here we copy SP into IDAL here during phi2. And we start the access. This is an M2T1. If we look here on push, SP out and status. And the status is AM right. Okay. M2T2 for the push decrements SP. We do not have wait states in M2T2 because it's a write, not a read. Okay, so we look something like that. M2T2, we are going to push our data out, which means that this guy needs to know what register we are. So this is not correct yet. On the diagram here, push does show RH showing up in T2. So there's two ways I can do this. I can add a M2T2 table, or I can just do the right thing in M2T1, which means that we end up having all of these replicated for each of the things. So let's do that. So all of these are going to be RP. Well, we knew it was going to get ugly. That's okay. We'll do this to avoid having yet more interaction tables. I'm going to make sure that my macros are similar in style. So now we have a pound define name push M1T4 of RP is going to be I8080 push M1T4. So let's put the RP in here. No, we always add it to the end, don't we? Okay, and defin push M1T4 of the register pair is static, F8080 state of too bad I can't use a macro to build a macro. M1T4 becomes M2T1. And 1 becomes 3. So we've got M1T4 and T5. We've got M2T1, 2, T3. And then we need there. And welcome to macro hell. Now where we're defining them down below, I'm going to use the, I still have it, I should go back and take all the places where I have this construct, which can confuse the indenter. And I'm going to change them all eventually over to something like this. Pound define, decal, push M1T4 of RP, and impl. So the reason why this doesn't confuse the indenter is because it's all on one line. It's all part of a macro. The indenter doesn't try to do anything on the line before and after based on what's this line. So this is a good place to put that confusion. So there we have it. And inside this, let's set up our macros initially to just do nothing, and I will then fill them in. So we switch phase. There we go. And let's get rid of all of this and start over again. change 4 into 1, 4 into 2, 4 into 3. Lots of boilerplate. You can see why people moved to doing templates under C++. M2 becomes M3. There we go. We define these for each register pair, and then we will need to do a specialized definition for doing the register pair that's not two 8-bit registers. That is, when we're pushing PSW, special shit happens. Now, RP is not really RP, it's H and L. Yeah, I forgot about that, and pound pound RH, comma RL needs to be pound pound RH, pound pound RL. Okay. I agree, Max. So, what I'm going to do for I'm going to put the macros first, and then I will just do all of the impl calls. So we'll do all of it for BC. We'll do all of it for DE. All of it for HL. Now, if I had a register called F, I could do it for AF. What we'll have to do is create the programming for PSW. How much of this? Just to be clear, when I push PSW, the first byte that goes out, the high byte, is the A register, and the low byte is the flags register. So if I do this, then I just have to specialize for the ones that actually use F rather than having it in the name. I can call the function AF rather than PSW. It's not too bad. I believe AF is where the operation code is where the terminology went when you went to the Z80. If things get too bad, I can muck with the names. Yeah, let's use PSW, and comma F becomes PS, comma W. They're going to get token pasted, and where we try to, we do have a W register, don't we? PS, comma W, let's go P, comma SW. So we don't have a P register or an SW register, so we'll do that. That will give us the proper names, and where the macros talk to the high register or the low register, we'll just have to specialize that in place. So push M1T4 is now a table. Which I am going to set up here to look like one of these tables. Okay, so push M1T4 undeclared here. Thought a function, did you mean push M1T4 lowercase? Well, this is uppercase. That's because I didn't put the declarations up at the top. So we need to call defen for each one of our register pairs. Oh, there's a tab there, isn't there? No, there isn't. Search for defen. As below, I am going to, oh, wait a minute. Pound define defen push BC RHRL. I may not be able to use a macro to define macros, but I could sure as hell use a macro to call them. Okay, so now we have a whole bunch of unused parameters. Do we have a redefinition? Yes, we do. Top level does not allow semicolon at end of function, which means all of these functions that I'm declaring, I almost forgot, they need to have an extra defen push M1T4 of RH, RL at the end. That will resolve some of it. So we're going to search forward for void decal underscore. We're going to capture that up through that. We're going to go to the close brace. We're going to set a backslash there, and then we're going to say defen underscore that. And I forgot to capture the argument list. Try that again. Start keyboard macro, void, oops, void decal underscore. Could grab all the way through the end of the line. And this is going to be defen, like that. And let's run the indenter line by line all the way down. So we still have these unused parameters. Let's set those up really quick. So we're searching for a switch phase. And I'm going to come in here and I'm going to say void CPU to do impl void phase do not fall into the trap of using line macros, or comments to end of line in macros. If you have a comment to end of line in a macro, you may find it expanding to do the wrong thing. For instance, It may trim the backslash off the end, so you may not see anything after the start of that comment. Or the macro may include the comment, and you may see the // and the macro processor may trim the backslashes, turning it all into one line. We do turn it all into one line, so error codes will have the line number correctly for the place where you call the macro, in which case you're commenting not just the end of this line, but all the way through the end of the macros. So a // here is really super duper bad. And I have messed up. There we go. So try this again. Switch. I hate it when I forget to move my cursor at the end of the macro so that it will go down to the next one instead of reapplying it here. There we go. So redefinition. Def and push. What is it doing there? So we do the def and pushes here, which say static name semicolon. And then we come down here and we say static name parentheses. So we didn't have any spare semicolons, did we? No, we didn't. Redefinition of push in that macro. Expansion of decal push. Staring at it very carefully. Oh, RH. Oh, that's RHRL. That's correct. So I'm wondering if I need to do something to run the C preprocessor on these files and look at the output. Because this is saying redefinition of push M1T4 RHRL based on expansion of this macro here. Oh, I wonder if somehow RH and RL are going in as RH and RL rather than BC and so on. There was a trick that we had to pull at one point back before preprocessors got clever, where if you wanted to use a macro inside a macro, but that was mainly if you wanted to use the stringization. So if you had like a #Z in a macro, it would expand to the name of the parameter unless the parameter name was expanded explicitly. Yeah, I think I need to do a pre-processing thing. Let's see here. Can do make file rules. Let's make a pre-dir. So I can do this on command. Now I'm not going to, well, So pre-processing, we're going to generate an .e file. You do that by putting in -e. In place of the -o, I think. So now if I do a make pre-i8080 underscore stack.e, there we have the preprocessor output for this guy, which includes all of the frippin' headers. So we are looking for this place where we are redefining this function. So I'm going to search down for i8080 underscore push M1T4. Push M1T4. Push M1T4. Oh, wait a minute. M1T5. There we go. The name is wrong. M1T4. So M3T3 PSW defined but not used. So we're going to keep this file up to date for the moment. So this is saying there's something weird about this guy. So we are statically defining it here. Actually, I think I'm going to change this. So when we do the pre-processing, I think I can just do this, which means I can also pass through indent -st. There we go. So that re-indent, that runs it through indent. So this is all showing me what's going on here. And now I can search for this function defined but not used. M3T3 PSW. Oh, none of these functions are, none of these functions link to each other, so they're, defined and not used. Fine. Valid. Fair cop. Okay, so let's take a look at what we have to do. So M1T4 for a push. And I just realized my macro expansion's behind the PDF file, which I neglected to turn off. But we need it on now. So push. Push RP. So T4, we get SP into IDAL. Back to where we were going before. So data to CPU arrow. Get the indenter to do things for me. IDAL is getting CPU arrow SP. And CPU arrow state next is equal to, actually let's macroize this. I'm going to search for phi2 fall and set it up so that everybody links to the next one down in the list. Search for phi2 underscore fall. Then we're going to search for name. And there, we got that in the buffer. And we say CPU arrow state next is equal to that name. Just like that. And this last guy, instead of that, is going to go CPU arrow, what's the red M1 contact thingy again? Red M1 int. So this last one will do that. So data to IDAL needs to be adder to, of course. And now I'm going to come in here and I'm going to fix all of my backslashes. I'm going to put them all in column 72 because I'm not trusting the indenter for now. Search for backslash new line. Go back to the end of the line and we put it out there at column 72. This takes a little longer. My little macro for placing something at a specific column is not too efficient because I don't usually use it in bulk like this. But that gets us something. Now if I re-indent something in the middle, it's going to match it up with the guys above it and below it, even though it could be narrower. So what do we have here? M1T4, we get SP into IDAL, and M1T5, we put there. And this is SP arrow value. And I need to make sure we're indented properly, along with having the backslashes in the right place. That gets the CPU state next stuff in place. There we go. Okay, so now we are compiling without warnings. Each one of these states essentially is doing nothing and handing off control to the next one. Hallelujah. Right. So back to the PDF, which we still have up. SP is SP minus 1. I already implemented that in T1, M1T4 and M1T5. That's correct. And state next is heading on to M2T1. So let's look at our second machine cycle. So here's M2. M2T1 is we are sending the stack pointer out as our address, and we're doing a whole M1 thing. So behind the PDF, I will bring up the source i8080 mov.c, and we'll look for the mov-m stuff. We're looking for T1. This is going to be a T1WR. So M2, T2, all these are going to need better comments, but this is M2 is a write byte to stack cycle. So copying from elsewhere, we have on phi2, we want to set the IDAL to the address we're going to, which is CPU arrow SP arrow value. We latch IDAL into the address bus. Our status is SWrite. And we are turning on sync to say this is the status that we want to send. And that compiles. And then during T2, we drop sync. And we write our data. And this is the RH. So this macro is going to have to be specialized for the stack pointer. And I can do that easily enough. Actually, for the PSW. Now, the first byte of the PSW push is the accumulator. Let's check that. PSW, here. Yes, the A goes out first. So the comment on this is specialized decal push for PSW. I-8080 push M2 T3 RH RL undeclared. Did you mean push whatever? In this macro, because I don't have RH RL, I need to put in PSW. Redefinition of M2 T3 PSW. Hold on. Let's take a look at that. I-8080 push M2T2 PSW. Does not appear. There we go. It does appear in the E file. Let's turn off the PDF momentarily. So we are declaring it here. And we are defining it here, M2T2 PSW. And we are defining it here. Well, that's no good. Oh, right. In fact, so the question is, do I want to leave this specialized version here or put it down below? I think I need to put it down below. There. That's better. Well, what? Why did it do that to me just now? Yes, edit the buffer. Save that. That's better. I don't know why it deleted all of that the first time through. But I am going to replace this with the actual name. I suspect that we had indent writing to it exactly at the same time Emacs was writing to it. So we got down to M2T2. M2T1, M2T2, puts our data out. And let's go back to looking at the i8080 mov.c and put our PDF back up real quick. So M2T3 for push is the final bit of the write cycle, so we're just going to grab all the work that was done here. So M2 T3, during phi 1 rising, we turn on red M1, except we don't because we have an M3 cycle, so we turn on write. And on the fall end, we're going to turn off write, and we're going to tri-state the address bus. Okay, now M3 is similar, but we're going to be working with the low register. So I think I can just basically copy M2 to M3. Like that. And this one gets a red M1 int. We are writing the low register, so this is RL. And we need to deal with the PSW bit here, so it's in M3T2. And there we go. It compiles without warnings. How about that? Now this is a lot more code duplication than I expected. And what it does for us is it means that we don't need to set up M2T2 and M3T2 tables in the CPU and then have our functions indirect through them. So we are trading instruction space for data space. Now we're using macros, which is C's equivalent for C++ templates. And anybody that says, "Oh, C++ programmers shouldn't use templates," tends to get laughed out of the room. So remember, this is the way that we did templates in C. I'm going to try to collapse this a little bit. We still have to specialize these guys. And I'm going to keep all the macros in one place so it's a little bit easier to read. And again. Okay, so it's just Emacs that was confused about that. Interesting. So I reverted it, and on disk it was correct. Oh, Emacs must have reverted the buffer while indent was still writing it. Got it. The the thing in Emacs that automatically updates a buffer from a file when the file is modified sometimes can conflict with somebody that continues to write the file. And you notice we ended up there with a partial, and we ended up with the buffer marked as modified, so it stopped updating it. Any other repeated things that I can bop out? Yeah. Now, I've had some ideas on how I can get rid of this phase stuff here, but none of them do so without a whole bunch of extra work. By which I mean additional actual runtime cost. There's probably ways to do it that don't have additional cost. I just haven't worked it out yet. So supposedly this has push and pop going. So I think I need to take a quick bio break. I will be right back. So the rule that people were starting to enforce right near the end of my career, and this is mainly pushed by the engineers, it's a great thing, is you need to take a break about every hour. And I am really bad about that. Now, I am starting to break up my other streams. I've got some gaming streams I do, and I'm starting to try to do those in about 1 hour chunks. So I may do the same thing with the coding. Unfortunately, the temptation there is to spend an hour coding up a feature and then break the stream, and when I come back, not actually do all the testing. So either it means doing smaller features and getting the feature and the test done in an hour, or it means absolutely committing to spending, an hour doing the feature and then how many ever sessions I need to construct the testing for it. Anyway, so now we're ready to start testing push and pop. Test. This is going to be similar to MOVM test in that I will have a test program that I run, and I will be checking results. I will be comparing the contents of memory when the results are done. So what I want to do, the test strategy I'm thinking of, is to pop some things into the registers and then push them back to memory and then verify memory got what it's supposed to get. So let's write the ASM for that. Start with MOVM test. Let's see, this is stack test.c. Test for push and pop instructions. This test is still being used before we deal with shadow, so it can only read the shadow ROM, and writes will go to the shadowed area. We're starting at 0, and why did I call it stack test.c? It's an ASM file. And what I want to do is LXI SP some area that will have data. And then I'm going to say pop BC. Actually, let's PC DE HL and PSW. Then we're going to push PSW HL DE BC. I am going to do an RST2 there so we can get a single plot which is going to have all of that. Now each one of these guys, these are 3 machine cycles each, so this is a very wide plot. And we may break it up a little bit further. And at this point we are done. So RST1, nop, 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 halt. Just in case. So following that is the data that I want to put into the registers. And so pop is read byte and increment, read byte and increment, read byte and increment. So data is going to be, how about 11H, 122H, 334455. Now this is going to be special when we're popping. I haven't written pop yet. Okay, got to write pop. But let's do the test. Let's do the test. And when we push PSW, we pop PSW here. Let's turn on the PDF. I want to get the data in the right place because the flag word is going to be interesting. Certain bits of the flag need to be forced on and certain bits need to be forced off, and I'm going to test that by putting the bits in that need to be forced. Okay. So pop PSW, the first byte popped goes into flags. So flag word. So let's look at the PSW thing here. Whoops, I seem to have messed up my PDF reader so that it's not doing page by page neatly. Oh, I'm in a search window. There we go. branch, return. So pop PSW ignores a bunch of bits. And push PSW is going to force a few bits. And specifically, this goes from low to high. So 2, so 0, 2 is going to be always high. And bits 3 and 5 are always low. Turn off the PDF. PSW bits always written high is 0, 0, 0, 0, 0, 0, 1, 0. And this is, okay, so what I want to do is have a data word that has those bits flipped so I can verify that they are being mangled properly. So I want 1101, which is a D, 0D, and I want 0. Actually, let's have all the bits, all the flag bits off, except that these bits are going to be the wrong way. So 0 in the top bit, that guy's a 0, and this guy's going to be a 0. That guy's no, it's O. This is going to be a 2 and a, actually 2, 8. That'll do it. Okay, so this is our test program, which uses pop, which I have not yet written. Okay, pop. So we take all of this push stuff, and pretty much it's going to duplicate into pop. And what are the differences? Let's bring up the PDF and look at the differences. Pop. So push mangles the SP during T1, M1, T4, and T5. Pop does nothing. It's going to increment instead of decrement. It's going to read instead of write. Got it. Simple enough. So it does not have a T5. It does have a pop. We're going to need to do pop instructions. The pop instruction is C1, not C5. Okay. Okay, so pop M1 T4 BC is declared somewhere, and is undeclared because I didn't do the def and stuff. didn't do the... let's move this up and move these up. So I've got all of our static declarations, and then I have our tables. So, used but never defined. Yay, that's what we wanted to see next. So all of these things where we are pushing, I'm going to grab this whole thing, duplicate it, narrow it, change push to pop. And that would actually knit it all together, so a pop instruction would now do exactly what a push instruction did, which is exactly the wrong thing. And of course, we don't have M1T5s. So we can go all the way down like that. Data definition has no type or storage class. M1T5. Got it? Hold on. I widened when I shouldn't have. There we go. So now if we were actually to run that program, our pop instructions would just do a push instead of a pop. So we do need to fix the pop instructions to do the right thing. So M1T4, we're not mucking with it there. We are, however, working with it at M2T1. So PDF goes up and gets moved off to the right a bit so we can see it and the code. So pop, double check M1T4 is doing nothing but delivering us to the M2T1. And pop then says SP out and increment. So M2T1, here is SP going into IDAL, and we are incrementing it back during T2. Hold on. I don't think push was writing back my SP properly. So here we have SP going into IDAL. Oh, here, and M1T5 was happening, but M2 also needs to write it back. So push was wrong. Push needs to write it back at M2T2. So pop M2T2 also needs to write it back with +1. Is that correct? Pop, yep. M2T2 does the +1, T1 does the SP to IDAL, IDAL +1 to SP. Now this is a read because we're doing a pop. So I am going to go grab I8080 mov.c. We're going to look at the mov-m. This is the mov-m to T2RD. So IDAL adder, we do need to set our status here. This is the sread. Sync goes high, sync goes low, data gets set up, which is no longer true. That gets a data Z. And we edge high, dbn. Now this does mean that we need to have T-wait states here. I am bringing up the move instruction behind the PDF so I can compare source code really quick. So T1, IDAL, adder, data, and sync. Next. T2, data, sync, data Z, sync low. I'm going to defer that and hit DB in. And now the thing here is if ready, then we're going on to the T3. Otherwise, we are going on to the TW. TWs are like T2s with some changes. For instance, they CPU db in value is equal to 0. Let's copy the comment from the MOVN stuff. And we have this same T weight. So M2 T weight, so this guy, to T2, we need a M2 TW. We're going to need M3 also to do that. So TW, oh, almost forgot, he needs to assert the weight signal like that. And that means that T3 needs to turn off the weight signal. We are not doing a write anymore. So during T2, T1, T2 read, T weight read, M2, T3. Okay, T3, we turn off weight. This is not a ret M1, so the thing that reads M over there that I'm referring to is actually a terminal cycle, and we are not. However, we do need to do the normal thing during Phi2 rising, which is data to the register, which is RH. Drop DB in, Z the address, and then we move onward. Now M3 is just the same as M2. I can just copy the M2 to M3. And this one differs in that at the bottom, we're moving into RL, and we are doing the red M1 int thing. So these guys, again, we will work out which ones need to be specialized. So this has to be specialized. And this has to be specialized. So impl pop M2T3 looks like this. So M2T3, again, we're going to go back to the PDF. This is pop PSW. M2T3 is reading the data into the flag word. Now we actually are going to ignore some bits going in, and we're going to set some bits going in, so we always correct the data coming from memory, or actually let's go byte F to 8, I think that was. Yep, 2 OX20 ignored during pop, write 0 during push. There, documented. Pop M2TWBC never used. M2 T2 oh, right. Used but not defined means I just didn't put it in here. M2 TWPSW, because I forgot to do these. And M3 T3 PSW still needs to be specialized. So this guy did F, this guy does A. That's all correct. I want to expand these macros. And the easy way to do that is to go back and look in pre can just go down to the bottom and grab these guys. Just like that. Now one last pass with the indenter to get the backslashes lined up. I'm going to leave these backslashes out there in the column 72 because it frankly doesn't matter. I do need to go back up to get everything lined up. Actually, let's put all the backslashes in column 72. Search for backslash new line. Let that run. Emacs is running my little macro over and over and over forever, and it's slow. And I think that's, yeah, it's just these impl pops where I change push to pop, and there's one more byte to go here. I think the auto indenter will pick it up from the line below. Yes, it does. Everybody else is good. And we got re-indented. We're looking good. File's kind of big, but there we are. Okay, so ASM. There's stack test. So stack test will now push a bunch of things, pop a bunch of things from here, and then push them back into memory at that location as well. I think what I want to do is put data at a known location. Org OO. Yeah. So put that at 100 hex. Actually, let's put it at 80 hex. Okay, PDF can go off. And there's stack test. That's better. It's not important, but if I can keep my LST files from getting too horrendously long, I'm a little bit happier. So there is the test program. So we want to go into i8080 stack.test stack underscore test.c. Thank you. I'm going to do a little make a clean dance so that we get rid of the bad named stuff. There. Let's make one last check. These are being executed. They are. Load stack test.hex and run it just like the others. Yeah, replacing the whole thing. I just copied Mavum and changed Mavum to stack. My goodness, what is it doing now that I've done that? Well, obviously it's going to fail on the test conditions because we aren't doing that. So what I might want to do is also compare that the surrounding RAM area did not get modified. So RAM test area size is set to 256 bytes, so that's a wide-ranging area. So if I is less than 128, we're going to say it's got to be the same thing. Okay, so we've got the unchanged stuff coming up to 128, and then we've got the unchanged stuff after where we do our testing. Else if I equal to so 128, 129, 130, 131, 132, 133, 134, 135. These are byte, 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 low, high, low, high, low, high, low, high. And they will be written out in the appropriate order so the data matches. So this is really the B register is going to get this guy. Wait a minute. Hold on. Checking. When we pop the low and then the high. And when we push the high and then the low. Let's make sure I did that right. So push. We push high and then low. So push M2, T2, PSW. No, specialized. I need this guy. Yep, push high. And then in M3T2, push low. Good. Now pop. Make sure we got these right. Pop RP. We're supposed to pop RL first. There we go. RL, then M3, pop RH. And the PSW specializations, we pop PSW, we pop the flags, and then the accumulator, and the push PSW, verify that, push the accumulator, and then the flags. So that's correct. So that's because I set these up as dBs of 2 bytes, low or high, rather than saying a DW of 2211 hex. So I would have had to have said, well, the PSW is 7728 because the A is pushed as the high byte. No, is the second byte. Yes, high byte. So that just ran the test, even though I don't have, oh, I set up all these cases saying we're going to do something. So case 134 is going to check to make sure I wrote the flag word. Assert EQ integer. And the flag word I'm going to get back, not 28, is going to be 02 hex. Actually, let's comment these guys out for the moment. I want to see failures here. And I also want to see all the failures. So we're going to go back into source support.c, and how we have the fail here, we're just going to say don't abort, thank you. And we're going to say, oh, this is failing because we are seeing these values. So first one, we're seeing 1, 1, and then we're seeing 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, 0, 2. And hold on. I don't think that wrote the PSW. I don't think I didn't write the final byte. That's the specialization here in M3T2 is not getting called, is it? Specifically M3T2 for the PSW. Ah, that's reversed. No, that's push. That is push. What am I missing? Let's take a look at the diagram I dropped. So stack 1. That's no good. I-8080 stack test.c. So we didn't crash out early. Well, that tells me that I didn't finish this function properly somewhere. Are we actually getting there? Top. And we are getting to the bottom, which means that somebody should have been writing those sig plots. Oh, right. PNG file doesn't get automatically removed. So rm doc img i8080 underscore stack star PNG. There we go. There's stack. And there is doc img stack 2. So here's a bunch of pops. We can see data coming in CB, ED, LH, flags in A. And sync pulses look good. Red M1 looks good. Data bus in looks good. So we are reading all of this stuff in. And the flags are getting the 02 value. And push is going out. Readies are dropping during the opcode fetch. That's good. There's M1s. There's our sync pulses at the beginning of each machine cycle. And there's the data. So the data should be the reverse of the above. So we see the 7702 being written. And the addresses during those write cycles are 8787. Addresses. Right. So the stack pointer isn't getting manipulated properly. So 88, 87, 86, 85, 84, 83, 82, 81. That should end up with a stack pointer equal to 80. So somebody is not decrementing the stack pointer during the pop. Pop +1 here. Phi 2 rise. Pop N3 T2 here, so that is happening. It does get incremented during T2, so it's read in T1, incremented in T2. Take a look at all the places where I look at the IDAL value. M1T5, we are decrementing SP. M2T2, we're decrementing SP. M2T1 of pop. We're using it, and then we are incrementing it into SP, using it, and incrementing it into SP. So I don't know why this is doing what it's doing here. Each instruction is moving by 2, 8, 7, 6, 5, 4, 3, 2, 1. I think I just need to have another NOP on the end of that to see what's going on. Let's toss another NOP at the beginning and end of each one of these. I don't need one here. Four, 5, 6, 5A. So we're not getting the final byte written to memory. Right. And the data bus during those writes is 7702 6655 4433 2211. So those are being written. The address bus is 8765. Well, that's pretty clear that we are writing the PSW, both bytes of the PSW are going to the same address. So there's still something very wrong there. So this is the pushes. So let's see, 87 should get tucked into IDAL. And IDAL is not getting latched here. So SP into IDAL. IDAL decremented goes into SP. During M1T5 of the push cycle. 88. So 87, and it goes out. M2, SP into IDAL. Oh, here it is. Nope, that's correct. Decrement SP, use the SP as the address here. Decrement it back into SP. We use it here as the address. And we're not writing it back here. Okay, so when is it written? During M3? M3, push RP. It's not. We should be decrementing it twice. Once in M2, M1, T4, T5, and once in M2. Okay. So M1, T5, we're decrementing SP. And M2, T2, we're decrementing SP. And it is specialized for PSW, and we're not doing it. There we go. So this is what we were supposed to specialize, and we lost one line of code right there. Yay, testing. So now we see our 7.7 showing up and our 0.2. And now we can finish with our test. Oh, come on. These should actually be insert EQ to the ROM sub 0. There we go. Print top and print end go away. And now we are silently passing the entire test. And here are our push instructions here. See the stack pointer, 8.8 down to A0, 8.0, perfect. And stack 1 is our pushes, or our pops, 8.0 up through 8.8. Why is stack pointers at 8.080 here? I don't know. Oh, that happened to be what we were there, just garbage before the test. Let's fix that up before we start. Data, adder, Z, CPU, arrow, SP. There. So the LXI is going to put in one byte at a time. So the 8.0 goes in, then the FF goes in, we're good. Just for fun, I am going to zero out also. I'm going to Z out the B, C, D, E, H, L. So we can see as the data arrives. There we go, nice and clean. So there is push and pop all done. And I think that's enough of a chunk of work to call it a day. I could, yeah, let's duplicate this up to post. Same thing, but no trace. So we start peeling this stuff out that we don't need. Dun. Okay, so we have a power on self-test for our stack, which does this same pop a bunch of data, push it, check to make sure the right data end up in RAM, we're good. This is not a sufficient test. For instance, if we were building a real chip with real gates, we would want to do a lot more testing to verify that each individual gate was working. However, we do not need to verify that our simulated system is working properly like that. PGNO is being used in BIST, and it is not there. Okay, so we're good. Let's turn off the PDF. Do we still have GitKraken available? I may have killed GitKraken off. Nope, it's right there. Okay. Try turning it on again. There we go. View changes. This is add, stack, and push, and pop. And stage all changes, and oh, we need to update this guy to move these into implemented. I will do that right here behind you. Doc i8080.org. Push and pop are no longer not yet implemented. There's some other things that I have hooking up the plots into the doc file as well. 8, let's see, MovM 9. Here we go. So if we temporarily hide GitKraken, I can show you what I just did. So here in the i8080.org file, we're documenting that we do have ALU ops on memory, and we don't see much. This is just operating inside the accumulator, really. We do see wait states as we read things, but there were just the two of them. The captions are wrong, that's all right. And push and pop, those are our new diagrams. And not yet implemented. So XTHL, load accumulator, store accumulator, LDAX, LHLD, STAX, SHLD, call, return, and restart. And that will do it. Back to this guy. He's staged. Also, provide, make rules for building pre/foo.e preprocessor. Stack test, impl gets stack, target gets some documentation. I don't want to commit those guys. Okay, so that, I guess I need to explicitly do a git add dash dash force on the git ignore file. There we go. Turn on stack, turn on stack. We are going to unstage that hunk, and we are going to discard that hunk. And before I do a commit of this, because I've modified it, I'm going to check. And we look good. Oh, I need to commit the new PNG files, don't I? Yep, there we go. So apparently, I didn't add these files before. Oh, hold on. Doc I-8080. Yeah, those are new files. That's 10 through 15. Yeah. So we're including those files in our document as well. Commit and push. Not sure why my pushes to GitHub are taking so long today. So he can continue in the background. Oh, done. Update available for Git Kraken. I'll take care of that offline. And we are done.